So today we have Chirantan, who will be telling us about complete Segal spaces as a model of higher categories. Take it away.
Great. Thanks, Sarah, for the introduction, and thank you for organizing this seminar and for everyone for joining it. Before starting, I'd like to thank my supervisor, Nima, for introducing to complete Segal spaces. So I'll be talking about an important model of higher category, namely the complete Segal spaces, which was introduced by Charles Resk in 2001. I have divided my talk into several parts. In the first part, we are going to look at the basics of category theory, and then we are going to see that why it's not enough to just have category theory and why we need to move to high category theory. Then we are going to look at some of the important developments related to high category theory in section 3. And in section 4, we are going to see that how we can obtain simplicial sets from the nerves and from the singular complex functor. And we merge both these ideas together to form simplicial spaces. And on top of which we apply a couple of model structures in section 5. And then after a bit of tweaking, we finally arrive at a definition of complete Segal spaces in section 6. Section 7 is entirely new and it's based on my preprint, which is in archive, and I think it's in the mail which Sarah sent everyone. And it talks a bit about the twisted arrow construction. Right, so let's start with category theory. So we'll define a category to consist of a class of objects, which will denote by little letters X, Y, Z's, and so on, and a class of morphisms, F from X to Y, such that this morphisms has the composition rules defined on them, such that for every X, there is a unique identity morphism from X to X. And if you have a morphism F from X to Y, then it has a specific source given by X and a specific target given by Y, such that the composition obeys the associative property. For an example, let us look at the category of finite ordinal numbers, which will denote by delta, where the objects are ordinal numbers, which will denote as ordinal 0, ordinal 1, and so on. We have a morphism from ordinal number n to ordinal number m if the ordinal number n is less than or equal to ordinal number m. And if we have two morphisms from ordinal number n to ordinal number m and another from ordinal number m to ordinal number p, then we'll say that we have a morphism from ordinal number n to ordinal number p if n is less than equals m and m is less than equals p by transitive property. For every ordinal number n, there is a unique identity morphism from n to n, which is given by the reflexive property. If we have a morphism from ordinal number n to ordinal number m, then the source is ordinal number n and the target is ordinal number m. And finally, it's easy to observe that it obeys the associative property. Right, so let's see by an example that why we need higher category theory, for which let us define the loop spaces. So for a given topological space X, the base point, which we denote by little x, we define a loop space on the topological space X at little x as a set of all continuous maps from the circle with a fixed point to the topological space X with base point defined by little x. Now, at first glance, we think that this loop space forms a group where the composition is the concatenation operator. But at a closer inspection, we see that this composition of loops are neither associative nor unital nor has an inverse, so it cannot form a group. But all of these properties actually holds up to a homotopy. So the way to make things like loop spaces into groups is by moving to higher categories. So intuitively for us, a higher category would be a mixture of category theory and homotopy theory. And in this specific case, if we want to make loop space into a topological group, we need to move to the realms of A infinity spaces. So let us look at some of the important models in higher category theory. So the most famous model of higher category theory is the quasi-categories, which has been introduced by Brodmann and Vogt in 1973, and henceforth has been first studied by Andre Joel and later by Jacob Louis. Other models of higher category involve the simplicially enriched categories, topologically enriched categories, A infinity categories, Segal categories, and also the complete Segal spaces, which is introduced by Charles Resk in 2001 in his seminal paper, A Model for Homotopy Theory of Homotopy Theory, and has been later shown independently by Bertrand Toen and Joel and Tierney to form a model of infinity 1 category. Amongst others, my supervisor and I are also working on the complete Segal space structure. There is a different school of approach by Emily Riel and Dominic Verity to study higher category model independently, which they are developing on their paper of elementary infinity categories. Now, Julia Bergner has studied and compared several models of infinity categories, namely Segal categories, quasi-categories, simplicially enriched categories, and the complete Segal spaces, while Jacob Lurie has studied and compared the models of A infinity categories and topologically enriched categories. So although complete Segal spaces are easier to work with and they are way more versatile, but the theory has not been developed as much as the other models. For example, quasi-categories have been. The primary aim of my thesis was to fill this gap and develop an elementary introduction to complete Segal spaces. So let us start by looking at simplicial sets. A simplicial set is a contravariant functor from the category of final ordinal numbers to the category of sets. Using the Yonda lemma, we can define a simplicial set X level-wise as Xn is isomorphic to the set of morphisms from del n to X, which from now on will denote as home of del n, X, where del n is the standard n simplex. We'll also denote the phase maps by di, which takes xn to a level down, xn minus 1, and the degeneration maps by si, which takes xn to a level up, xn plus 1. A simplicial set looks something of this form, where there are two phase maps, d0 and d1 from x1 to x0, and one degeneration map, s0 from x0 to x1. Similarly, there are three phase maps from x2 to x1, denoted by d0, d1, d2, and two degeneration maps from x1 to x2, which are denoted by s0 and s1 respectively. As an example of a simplicial set is the nerve functor, which acts on a small category C, which will denote as n of C. And it's defined level-wise as the zeroth level of nerve are the objects in its underlying category. The first level of nerves are the morphisms in its underlying category. The second level of the nerve denotes a pair of composable arrows in its underlying category. And similarly, the nth level of nerve denotes the strings of n-composable morphisms in its underlying category. So the nerve functor takes any category and gives us a simplicial set. However, this list is not exhaustive. That is, we can obtain every simplicial set using the nerve functor. So the obvious question is, what kind of simplicial sets do we obtain using the nerve functor? And the answer lies in the following theorem due to Segal, which states that if X is a simplicial set, which satisfies the so-called Segal condition, then X can be written equivalent to the nerve of some arbitrary category C. Now, what does it mean to satisfy the Segal condition? So Charles Tversky defines a simplicial set X satisfies the Segal condition if the nth level of X can be written as the product of n copies of x1, which are joined along x0. As an example of a simplicial set which satisfies the Segal condition is the nerve functor, which is a trivial example. And it's easy to observe because if we replace x1 by nc1 and x0 by nc0, then the right-hand side is product of n copies of nc1 joined along nc0, which is exactly ncn by definition of the nerve. There is a geometric realization functor, which takes a simplicial set into a compactly generated Hausdorff space. As an example, the standard n simplex, the geometric realization of the standard n simplex is the topological n simplex, which is the n plus 1 coordinates in Rn plus 1, such that the sum of the coordinates is 1, and each of these coordinates lies in the closed unit interval, using which we can also write the geometric realization of a simplicial set X as the co-limit of the topological n simplex. There is also a singular complex functor, which is right adjoint to the geometric realization functor. We'll denote the singular complex functor by S, which takes every compactly generated Hausdorff space into a simplicial set. Now, just like before, this list is also not exhaustive. That is, we cannot obtain every simplicial set using the singular complex functor. So what kind of simplicial sets do we obtain using the singular complex functor? The answer is we always obtain a Kahn complex. So if we apply the singular complex functor on a compactly generated Hausdorff space, we always get a Kahn complex. Now, we call a simplicial set X as a Kahn complex if it satisfies the horn pillar condition. That is, if we have a horn lambda nk, which sits inside the standard n simplex del n, then it can be lifted to the simplicial set X. This is also known as the right lifting property. So let's observe what we have seen so far. So using a nerve functor, we can transform every category into a simplicial set, which is defined level-wise as XL is home of del L comma X. And using the singular complex functor, we can transform every compactly generated Hausdorff space into a simplicial set, which is defined as Xn is home of Fn comma X. Now, I make a distinction between del L and Fn so as to distinguish between from where I'm getting the simplicial sets from, where in the first case, my simplicial sets behave like categories. And in the second case, my simplicial sets behave like homotopies because I'm obtaining them from topological space. Right. So now we have two kinds of simplicial sets, one with categorical properties and the other with homotopical properties. So the usual way would be to combine them together and take the first step in defining higher category. We do so using a simplicial space, which we define as the functors from del op times del op to the category of set, and is defined level-wise as XNL is home of Fn times del L comma X, where Fn and del L are the ones as defined above. A simplicial space looks something like this, where x00, x11, x02, that is every xij denotes sets, and the columns and the rows denote simplicial sets. That is, the first column is one simplicial set, the second column is another simplicial set, and so on and so forth, where each of these columns are generated by Fn, while the rows are generated by del L. So the entire simplicial space is generated by product of Fn and del L. Right, so before we move to model categories, does anyone have any questions?
Sorry, real quick, I missed it. What was the F functor again?
Yeah, so the F functor behaves exactly like del L, except that my Fn is actually a discrete simplicial space. So I have not properly defined them, but it behaves like del L, just it's discrete.
All right, thank you.
Sure. Right. So let us define the Reedy model structure. So if we have two simplicial spaces, X and Y, and a simplicial map from F from X to Y, then the Reedy model structure on the simplicial space is defined as the fibrations are maps F from X to Y such that level-wise, the kth level of Y, the map from kth level of Y to the kth level of X times the boundary of the kth level of Y joined along the boundary of the kth level of X is a fibration of simplicial set. Now, co-fibrations are monomorphisms, that is level-wise, the maps Fn from Xn to Yn are injective maps on simplicial sets, and our weak equivalences are defined as level-wise weak equivalences on simplicial sets, that is, they are Kahn equivalences of simplicial sets. If we have a simplicial space given to us, then we would say that X is Reedy fibrant simplicial space if level-wise the maps from X to the boundary of X are Kahn fibrations. A trivial example of a Reedy fibrant simplicial space is Fn itself. If we have a Reedy fibrant simplicial space given to us, then we would say if Xn can be written as Kahn equivalent to product of n copies of X1 joined along X0, then we would say our X is a Segal space. This Xn looks like this, where D0 and D1s are the face maps, which takes X1 to its source and target maps respectively. And I mean, they are joined along X0, and this is this interior X0 here. So using a, since X is a Segal space, we know that X2 can be written as Kahn equivalent to product of two copies of X1, which are joined along X0, where the left-hand side is actually a two cell, which is given by the mapping space of X, Y, and Z, while the right-hand side are two one cells, which are given by mapping space of X, Y times mapping space of Y, Z, where a two cell looks like a closed diagram of this form, where I have a morphism F from X to Y and a morphism from Y to Z, which we denote by G. Then I can compose them and get a morphism from X to Z, which is G of F. But on the right-hand side, I have a morphism F from X to Y and I have a morphism G from Y to Z. Now, my Segal condition says that I can close this diagram, that is, I can have a morphism from X to Z, which I denote by H, but the Segal condition does not guarantee that my H is unique. That is, using the Segal condition, I cannot say that I can write H as G of F. So to do so, we define a mapping space as if I have n plus 1 coordinates, x0 to xn, then the mapping space of x0 to xn can be written as a homotopy pullback diagram, where the mapping space sits inside xn, and I have a confibration from xn to x0 to the power n plus 1, which are product of n plus 1 copies of x0, and this is a contractible space which goes to del 0. Now, since X is a Segal space, then I can write Xn as a Kahn equivalent to product of n copies of X1s, which are joined along X0. And this, since this is the Kahn equivalence and this is the Kahn equivalence, we have a commutative diagram of this form, using which we can write the mapping space of X0 to Xn as Kahn equivalent to mapping space of X0, X1 times dot times mapping space of xn minus 1, xn. Now we can define the composition function between two functions f and g to be inside the mapping space defined by x, y, and z, which as this homotopy pullback diagram, where by the last remark, we know that the mapping space x, y, z is Kahn equivalent to mapping space x, y times mapping space y, z, which are given by the phase maps D2 and D0, while so D2 takes functions from X to Y and D0 takes functions from Y to Z, and D1 is my H in last diagram, which takes functions from X to Z. Now, since homotopy pullbacks are, since Kahn equivalents are closed under homotopy pullback, then this one is also a Kahn equivalence, and hence comp FG is contractible. So we can write comp FG as those sigmas which sits inside X2, such that the D0 sigma is G and D2 sigma is F, and my H is G of F, since comp FG is contractible. Now, now that we have defined the Segal space, we would see that the homotopical properties and the categorical properties do not behave well with each other. To do so, first, let us define the homotopy category on X, which we'll denote by ho of X, and is defined as the objects of ho of X are the objects in my underlying category X. Morphisms of ho of X are denoted as if I have two objects X and Y in the objects of ho of X, then the morphism between X and Y are the set of path components of the mapping space between X and Y. And composition is defined in the usual way, where if I have a morphism from X to Y and one from Y to Z, then the one from X to Z is defined by composing G and then F and then taking the class of it. We can also define the space of homotopy equivalence by X ho equiv, which is a subspace of X1, where every map in X ho equiv is a homotopy equivalence. So now let us look by an example that why the completeness condition is necessary, or why the categorical and homotopical properties do not behave well with each other. So for which we define a category I1, which consists of two objects, X and Y, and an invertible morphism between them. Then categorically, I1 should be equivalent to the category of finite ordinal number 0, which has only one object. Now, if we consider the Segal spaces of them, then the nerve of I1 at the 0th level consists of the objects in I1, which are two objects, X and Y, while the nerve of the ordinal number 0 at 0th level consists of only one object. So although I1 and 0 are equivalent to each other, their Segal spaces are not. And the reason for that is because in the nerve of I1 is not level-wise contractible as the nerve of the final ordinal number 0 is. So we'd say that if we have two simplicial spaces x and y, then they would be equivalent if and only if all the levels are Kahn equivalences, that is xn and yn are Kahn equivalences of simplicial sets. But in our case, we see that at the 0th level, they are not equivalences, and hence the nerve of 0 and nerve of I1 cannot be equivalents of simplicial spaces. So we need a condition that guarantees us that if 2 points are equivalent in the Segal space, then they're equivalent in the objects, that is, they're equivalent in x0. And this is exactly the completeness condition. We have a degeneration map S0 from x0 to x1, which is factored by x whole equiv. So if S0 takes x to identity of x, then S0 is injective, but it can also be made surjective if we consider x1 to consist of all the identity maps. Hence, we arrive at the definition of complete Segal spaces. So we'd call a Segal space X to be a complete Segal space if the maps from x0 to x whole equiv are equivalents of spaces. As a trivial example, we would say that n of the nerve of C is a complete Segal space if and only if C has no non-trivial isomorphisms. To see the implication, since n of C is a complete Segal space, then NC0 is equivalent as a space to NC whole equiv. Now, NC0 and NC whole equiv are both discrete sets, and that's why they are bijection of sets. And that's why the homotopy equivalences has to be the identity map. And if the homotopy equivalences are the identity map, then C should not have any trivial isomorphisms. For the reverse implication, since C has no non-trivial isomorphism, then NC0 can be written to be isomorphic to NC whole equiv as sets, where NC whole equiv are the same as the isomorphism class of C, which takes x to the identity of x. And since isomorphism is a stronger condition than equivalence, then NC0 to NC whole equiv are equivalents of spaces. Right, does anyone have any questions before we move to the twisted arrow?
I've never looked at it. Is it easy to replace a Segal space by a complete Segal space? Like, is it a relatively short description?
I'm not sure what you mean by replace a Segal space with a complete Segal space. So our goal is to form a model of infinity category, right? So now we see that the Segal space structure is not a model of infinity category because the Segal space has the categorical and topological properties, right? But they do not behave well with each other. And since they do not behave well with each other, in this example, for example, as categories, they are equivalent, but as spaces, they are not. So, and to overcome this, we apply the completeness condition.
Yeah, so if this is off topic, let me know. But what I meant was, I guess my thought is that like Segal spaces, form maybe a model category, and then going from a Segal space to a complete Segal space is like a vibrant replacement, maybe. So I was wondering, because I think maybe I heard kind of, it's complete Segal spaces, or maybe they don't come up super organically. So maybe you start with a Segal space which you can kind of describe pretty easily, and then you use some technology. But anyways, it sounds like it's off topic. So.
Okay. Right. So let's look at the twisted arrow construction. Now, if we have a category C given to us, then we can associate on C the twisted arrow of C, which will denote by twisted of C, where the objects are morphisms in its underlying category, where I would denote the objects as F from C to D, where C and D are objects in my original category C. The morphisms, if I have objects F from C to D and G from C prime to D prime, then I would denote the morphisms using a commutative diagram like this, where note that in a general commutative diagram, my K should go from C to C prime, but in a twisted case, it goes from C prime to C, and hence the name twisted arrow. Now, if I have two morphisms, then I can compose them and get in the usual fashion and get right K prime of K prime prime. Like I just compose the top arrows together and I compose the bottom arrows together to define the composition. Now, Barwick defined that if X is a quasi-category, then the twisted arrow of a quasi-category is a simplicial set, which is written explicitly as the init level of the twisted arrow category is isomorphic to home of del n, twisted x, which is isomorphic to home of del n op concatenated with del n, x, which is isomorphic to x to n plus 1. There is a forgetful puncture from twisted x to x op times x, which takes an object f from C to D in twisted x to C, D to the source and target in the underlying categories. Now, in our construction, we first construct the simplicial spaces, which we define level-wise as twisted x of Mn is x to m plus 1, n. That is, when we apply the twisted arrow construction to Fm, we get f to m plus 1. And when we apply the twisted arrow construction to del n, we get the identity, we get del n back. Now, note that this construction is not unique. That is, we could apply twisted x of Mn to get x to m plus 1, 2n plus 1. Where if we apply the twisted arrow to Fm, we get f to m plus 1. And if we apply the twisted arrow to del n, we get del to n plus 1. Or we could have applied the twisted arrow Mn to get xm, 2n plus 1. That is, if we apply the twisted arrow to Fm, we get Fm. And if we apply the twisted arrow to del n, we get del to n plus 1. Now, we have shown that all of these three constructions are equivalent to each other. So it makes sense to take any one of them as a working definition. Now, our main result is to show that if X is a complete Segal space, then the twisted arrow of a complete Segal space is a complete Segal space, which we achieve in 3 steps. First, we need to show that the twisted arrow of a redifibrant simplicial space is a redifibrant simplicial space. Then we show that the twisted arrow of a Segal space is a Segal space. And finally, we conclude that the twisted arrow of a complete Segal space is a complete Segal space. So if we have a redifibrant simplicial space X given to us, then we need to show that the twisted arrow of a redifibrant simplicial space is a redifibrant simplicial space. So for which we have applied the following equalizer diagram, where we can write the boundary of a twisted X as the maps from the boundary to the product given by x to n minus 1 and 2 maps to the product of x to n minus 3. Now, if you want to show that the twisted arrow is of a redifibrant simplicial space is a redifibrant simplicial space, then we need to show that the maps, the level-wise maps from twisted X to the boundary of twisted X are confibrations, which we obtain by replacing the boundary of the level-wise boundary of the twisted X by the above equalizer diagram. Next, we need to show that if X is a Segal space, then the twisted arrow of X is also a Segal space. So we have the following homotopy pullback diagram, where x3 times x3 joined over x1 can be written as the following pullback, where we have 2 maps to x3, which are joined along to x1. Now, since X is a Segal space, then x3 is con-equivalent to product of 3 copies of x1 joined along x0, which can be projected to the internal x1 by the third and the first projection map, where we are identifying this last x1 with the first x1 here. So we can write x3 times x3 joined over x1 as 3 copies of x1 joined along x0, which are joined along x1 to 3 copies of x1 joined along x0. Now, this is equivalent to a product of 5 copies of x1 joined along x0, which, since x is a Segal space, we can write as x5. Now, we know that x3 is isomorphic to twisted of x1, and x1 is isomorphic to twisted of x0, and x5 is isomorphic to twisted of x2 by the twisted arrow construction. So we have a Khan equivalence from twisted x2 to product of 2 copies of twisted x1 joined along twisted x0. Finally, we show that if X is a complete Segal space, then the twisted arrow of a complete Segal space is a complete Segal space. So the main proof idea is to first to show that the twisted arrow of a homotopy category of X is equivalent to the homotopy category of twisted arrow of X. And then we show that we have a pullback square like this, where we, by the degeneracy map, we have a map from twisted x0 to twisted x1, and we have map which are factored through twisted x whole width. And at the bottom, we have the maps from x0 op to x1 ops, which are factored to x op whole width, and another map x0 to x1 using the degeneracy map, which are factored through x whole width. Then if we take the product of them, then we have a map from x op whole x0 op times x0 to x1 op times x1, which are factored through x op whole width times x whole width. Now, since x is a complete Segal space, then x0 op is equivalence of space to x op whole width, and x0 is an equivalence of space with x whole width. So the product of them are also equivalence of spaces. Now, Khan equivalence is a closed under homotopy pullback. So twisted x0 is equivalent to twisted x whole width, as we wanted to show. So the twisted arrow of a complete Segal space is a complete Segal space. Right. Does anyone have any questions? Okay. If not, I'm sorry, but I've finished it. Maybe a bit ahead of my time.
So I have a question on slide 32. Yes. So what does the twisted arrow 2 being a product imply for
Sorry?
us? At the very bottom of the slide, what does the product imply?
This one?
Yes.
Yeah. So if you want to show that something is a Segal space, let's go back to the definition. Yeah. If you have to show that xn is a Segal space or x2 is a Segal space, then that x2 should be Khan equivalent to product of 2 copies of x1 joined along x0, right? So for the twisted arrow case, we should have twisted of x2 should be Khan equivalent to product of 2 copies of twisted x1 joined along twisted x0.
Okay, great, thanks. Any other questions? All right, well, let's take a moment to thank Chirantan